Welcome to the video. This is lab number 5 demonstration for ELEC 291, and this is a AC phase signals measurement meter, and let's see how the device works. So let's see the hardware first. And so the hardware is we have a microcontroller, a LCD display, 3 push buttons. This fourth one is the reset. Then we have 3 chips. This is a 7660 5-volt inverter which generates negative 5 volts, and then we have a dual op amp which is KA358, and then we have a LM393 comparator which has 2 comparators inside. So and then we have 2 capacitors. Both are about 0.1 microfarads or 100 nanofarads, and they help smoothen out the pulse. So then we have some diodes to protect the input voltages for this microcontroller, because these cannot go below 0 and above 5 volts. So whenever the voltage is above 5 or negative like below than 0, then these help us and save the microcontroller. And so let's start. So this is basically a meter. So the test signal is over here, and for the signal generation I am using an oscilloscope and a function generator. So the blue one is the oscilloscope and the green one is the function generator, and these are provided to us by the university. And then we have so then we have a MOSFET over here, some resistors and some resistor over here, and an LED, and then we have a speaker for some extra features that I'm gonna cover later in the video. So let's begin to look by the start features. So right now the oscilloscope is the function generator is on, and as you can see we have a reading. Let's switch it off and see what happens. So let's switch it off, and okay, so as of now the signals, the display says invalid signals, which basically tells the user that the signals are not sinusoidal. Either they are exactly DC or there are no signals at all. And if you look at the oscilloscope, which is over here, and oh sorry, I'm not zooming. Yeah, so the oscilloscope are being one channel is here and the other one is over here. The green wires are for oscilloscope and the yellow wires are for the signal generation. And if you look at the oscilloscope on the screen, which is over here, you see a flat line which basically tells us that the signals are off. So there's no signal, and that's why this display says invalid signals. So let's turn on the oscilloscope and see what happens. So I'm going to turn it on. Okay, set generator, and we see signals. Okay, so right now I can see that the display starts working again. Let's see. Okay, yeah, so right now the test signal is set at 1.2 volts and the reference signal is at 2 volts, which I can show you at the oscilloscope if it's clear. So in the oscilloscope you can see the blue one is the test signal and the yellow one is the reference signal. And so the channel 1, or this is also called channel 1 and channel 2, and channel 1 is at 2 volts and channel 1 is at 2 volts and channel 2 is at 1.2. so we can see the same here. Yeah, so channel 1 is at 2 and channel 2 is at 1.2 volts. Yeah, so let's go and talk about how we work with the device. So when we boot this up like this, we see this, and it starts at the measurements. So these are the peak values to be noted, and these are not the RMS value. And let's see how we cycle between different modes. So there are about 7 modes in this device. So let's go on one by one. So 7 display modes. So when I press these 2 buttons, this button I use to cycle between modes, and then this is used to calculate entry to average mode. I'm going to talk about the average mode later. Let's look at the cycle modes. So these are being used to cycle between different modes, and we can go press, if we want to go to a mode forward, like the next mode, we can press this button, and if we want to go back to the previous mode, we can press this button. These buttons are being controlled using the I'm using the port match interrupts, so that whenever you press the button you don't have to wait for polling, and the moment you press it you can get get the value change. Yeah, as soon as the microcontroller finishes the thing that it's working on, and then the moment it is free, it will change the mode. I'll talk about why I said the moment it's free later. So if I press this button, I go to the next, and now we see the RMS values for the test and the reference signal. So the RMS values are over here, and we have a resolution of 2 decimals and 1 integer, or one place before the decimal and 2 place after the decimals. These are the RMS values. So let's change our input amplitude. So let's set the reference to about 2 volts. Oh, what it was actually 2. Let's set it to 1.5 volts. So okay. Oops, I didn't send. Yeah, this is the reference. Yeah. Okay. Yeah. So as you can see right now, both of the frequencies, both the signals are at the same voltage, and so that's why we see the same RMS values. Let's go back to see the values, and these are 1.45 volts, which is what I set on the oscilloscope. It's difficult to see, but here I can see it says 1.5, and this is the amplitude of both the waves. And so let me change it to, let's say 2.6, and yeah, so I changed the reference, and we can see the reference over here, 2.6 volts. So let's move on to additional next features. So now if we press this button, we go to RMS. Now we press it again, we go to frequency measurement mode. So right now the frequency is at 60 Hz and the phase is about 110 degrees, negative 110 degrees. The frequency is in the range from 0 to about 1000 to, no wait, not 1000, around 10,000 Hz, and the phase is from negative 180 to 180 degrees. So let's see, if I change the frequency, let me change the frequency, and we'll see the, so right now the frequency is 60. Let's set it to around 75, and we see 75.9 Hz. And if I go to my oscilloscope, as you can see over here, the frequency is around 74.78 Hz or 75 Hz. Let's change the phase now. So the problem with this is if you change the frequency in the function generator, the phase also changes. So let's set the phase also to 75 and see what happens. Okay, so we have the phase 75 degrees and the frequency as well 75 degrees. Now let's go to the next mode, and the next mode is phase and frequency in radians and radians per second. So in this mode, we can see the frequency, angular frequency, which is in omega, omega is used to denote the angular frequency. That's radian per second, and we have that as well. So if you want to use that, you can directly convert them. You don't have to do a calculator and then convert it manually. So when we go back, we see the frequency in hertz, and when we go again, so we can see the frequency in radians or radians per second. Now let's go and next. So let's see the max amplitude. So this feature is basically so from the moment the device boots up, it keeps track of the minimum and the max amplitude that the device has ever recorded. So as long as I started it, the minimum amplitude that the device recorded was around 1.8. This is the peak amplitude, and the maximum amplitude where recorded was 2.6. So which is right, because I set initially to 1 and to 2 point, and the highest point was 2.5 volts. So let's set the amplitude to around 3 and see what happens. So I'm going to change the amplitude to 3 volts, and okay, yeah, so see this thing updated, so telling that the maximum amplitude is now 3.6 volts, and let's change the minimum. So in order to change the minimum, you can either go to the minimum point or maybe boot the device again. So let's set the minimum point to 0.5 volts. So right now the channel is now at 0.5 volts, and if I press enter, yeah, so this is the minimum now. Let's look at the data plotting feature. So this thing has a data plotting feature which allows us to plot the signals and visualize them. This is I'm using a Python, so let me run it up. And okay, so we are on, and so let me change the amplitude so that we can view it better. Currently it's at 0.5 and 3. Let's change it to 2.2 and 3. So yeah, this way we can help. So now I would like you to have a look at the signals right now. So as you can see now, when I go to the data plot, I have a Python program running which is whenever we receive the plotting information, it will give us Python plot over there. So let's go to the plotting menu or mode. So press and plotting. So okay, yeah, so we see a chart, and this is the signal plot. Yeah, so let's take one more. So I just press, so I close it. Okay, yeah, if I press this one, and it will give me a new chart again. So it's not that it will automatically send the variables. You only, when you're in the plotting mode, you will see the variables, and you need, the software verifies it first that the data is actually right, and then only the data is being used. So we can see the signal plots in the screen. Let me increase the size of this plot. So right now the volts per division is 4. I'm going to set it to 1 volts per division in both, for both channels. And okay, so now we have something similar to that. So okay, so this is the Python plot, and this is basically the actual signals, and this is the plotted signals that we get using the data that we get. So if it's visible, we have the test amplitude, the reference amplitude, then the frequencies of the sinusoidal signals, and the phase. And so the blue one is for the test and the red one is for the reference. Same in this one, the blue one is for the test signal and the yellow one is for the reference. I didn't go with the yellow because it is not clearly visible on this white chart, so I just get with the red, that's why you see. But if you compare them closely, these are actually very similar. Let's change one amplitude. So let's set this to around 1 volts. So you can see the amplitude decrease. Now to get a new chart, you basically go into the plotting mode, and then you press this button. Okay, oh sorry, no, you press this button. Okay, now you close the initial chart and you get a new chart. So the way this works is when we press that button, we send a 1. Oh wait, yeah, we send 1, which the Python basically checks. When it receives a 1, then it knows that the next 4 serial information will be the information that we use, which is the amplitude of the both sinusoids, the phase difference and the frequency, and then we give then we get the chart. So as you can see over here, these are very similar plots. The yellow one is the reference signal, and the same reference signal, the red one, and then blue one is the test signals. And you can see here we get some information like the amplitude and the frequency and phase. So this was the plotting feature. That this can be, now after that what we can do is, like, we can save the figure if you want, like, yeah, so that you can have a look at what you get. Now let's move on to another feature, which is the data visualization feature. Okay, so this feature is actually quite interesting. So when we go into the data, okay, so we are in the max amplitude. Now we can go to the data visualization feature, and okay, so visualization feature. So what happens in this feature is, based upon the time period of the input signals, we create a PWM signal, and then the PWM is from the width, sorry, not the width, the actual time period of the PWM signal is the time period of the input signals, and then I vary the PWM signals from duty cycle from 0 to 100%. So we go from 0 to 100 and then 100 to 0. So okay, so we don't see the LCD exactly clear, but now I slow down the shutter speed, and so you can see that the LCD is like glowing and decreasing. Also I just noticed we can't see the speaker, so let me do a jump cut. Okay, I'm back, and right now, so what I did before behind the camera is I replaced the resistor so that we can have an audible output. So I don't know if it's audible, but I'm taking a guess and it's audible. So right now the frequency is around 60 Hz, and let me just shift it from the PWM. So okay, yes, so at this pin, which is pin number 14, we have a PWM signal whose pulse period is the frequency or the period of the input signals, and we verify. So if you look at the oscilloscope, you can see the PWM signal going from 0 duty cycle to 100% duty cycle, and then from 100 to 0, and that's what we visualize using the LED and the speaker. So now let's change the frequency to something else. So right now the frequency is 60 Hz. Let me increase it to about 150 Hz. As you can see, the frequency or the pitch of the sound change, which is inevitable because we change the frequency, right? The frequency is high, so we have blend, and you can see the change in the PWM signals as well. So I would like to focus on the blue signal because that's what the PWM is. And okay, so now let's increase the frequency to around 500 Hz. Let's increase up to 1000 Hz. So yeah, we can increase up to 10,000 Hz. After that we go out of the hearing range, so we can't hear anything. But if you can, let me know in the comments. Let's go to around 8000. That's around, yeah, this is around like the maximum which I can hear. So yeah, let's go back to around 200. Okay, yeah, so basically on this mode we can visualize the signal, and that's a cool feature to like help us like see how actually the frequency behaves. And now let's talk about the third button. So I didn't mention it. Let's see, this is actually the auto average mode toggle. So when you press it on, the system takes 50 readings and then take the average of that and then get the value. So say if you have some noise in your signals, you can use this mode to clear out most of the noise, and essentially I'm getting a reliable value. So if I press and hold, so the problem is that these two buttons are actually using port match interrupts, but this is not, because I was having less space to accommodate, because the pins still here from all the pins in this row and half of the pins in this row till here, like these pins have the port match but these pins don't, so I don't have a lot of space to accommodate the button, so I have to use general polling. So I have to press it and hold it, and it says average is on. So right now you will see that the value is 3.5 because we don't have a lot of noise in our measurement, as you can see from the graph. The blue line is basically the PWM output, so it's 0. So right now the yellow line is the reference signal, and since we have very less amount of noise, so we get exactly the same values. But to show that I'm actually updating it, I can go to so as you can see, the device becomes really slow because it takes time to calculate the 50 values and then take the average, so it's a bit slow. But if we go to the visualization mode, that's where we see the best visualization. You see the break, yeah, it's because the time taken. So if I decrease the frequency even low, so let's go to around 50 Hz. Now it's gonna take a lot of time to open. So 50 Hz means it's really slow to like, it takes a lot of time to get new values, and then you can see it's like taking a lot of time. Yeah, so that's the average mode. It basically gives you accurate measurements. So let's change it up. And if you remember in the start of the video, I talk about when we press the button, the moment microcontroller was free, then only it shifts. You just witnessed that. So if you press the button if we are in the visualization mode and then you press it, so it won't immediately go to the next mode because microcontroller is busy in this setting. So the moment it's free, you go to the next mode like this. So yeah, that was my demo for the phasor measurement and meter, and I hope you like it. Yeah. Thank you for watching, and I'll see you in the next video.